Shut up and sit down.
Well, hello everybody. Welcome back to Electrician Live. And my name is Paul Abernathy, and we're at part 2 of a topic that we've been discussing. If you haven't listened to part 1, go to our website, electricianlive.com, click on the podcast link up there, Pure Podcast, and you can re-listen to it. Of course, you can listen to it over on our YouTube channel. That is youtube.com/master the NEC. And you also can listen to our live broadcasts. Okay, we do live broadcasts too, every Saturday evening at 8 p.m. Central Standard Time. But of course, I obviously put out a lot more content than just the live. But again, I encourage you to go visit it and listen to it and share it with everybody. Thumbs up if you like it. Appreciate your listening. So we previously talked about in part 1 dealing with how to calculate the width of a cable tray, what can be in a cable tray, and whether or not it can be layered or based on whether or not it was based on a approximate area fill, or whether or not they're larger conductors and we would use diameter values and all this kind of stuff. And we did that. We kind of established it. We even learned some formulas that are probably pretty confusing for people because, again, cable trays can be, just be honest with you, pretty darn confusing. And usually the good news is cable trays typically will be done by a design engineer, and they'll use software and they'll plug in the information with the width of the tray, and it'll kick all this information out, and you ain't got to worry about it. But in some cases, we do have to worry about it. And in cases where we do have to worry about it, then we need to know what the values are and how we address it. So that's kind of what the topic was in this series, how we're going to address that. So we talked about all those items, and now we're going to kind of move into what I promised in part 2, which is dealing with ampacities of the conductors that are put in that cable tray. Now, of course, we've got cables and multiconductor cable, and of course, we have single conductor cables. And again, as you remember back from part 1, that single conductor cables, or now single insulated conductors, can be in a cable tray as long as it's an industrial establishment. And we kind of talked about what that was, and the NFPA 101 Life Safety Code kind of gives a definition of it. I'm sure IBC or IBC International Code Council also gives a definition of it. But again, there's good explanations on what it is. Easiest way to remember, if you're producing something, manufacturing something, if you're just selling it like a Walmart or a Target, that's not an industrial establishment. Just kind of using that as your guide. If you're making something, manufacturing, whether it's some kind of process, and I use the example of Encore Wire. We produce wire and cable. It's a industrial establishment. We produce a product. And, of course, we have, obviously, cable trays running all over the place. All right, so we're not going to rehash that. Go back and listen to part 1, kind of get you up to speed. Now we're going to talk about ampacities. Now, we're in the 2020 National Electrical Code. That's what this is. Again, how it equates to you in the 2017 code, again, is, for example, the ampacity tables changed a little bit. But other than that, other than the changing of some of the tables and references, the intent or the basic intent of how we're going to talk about didn't change. That didn't change at all. And Section 80, which is dealing with ampacity, is not overly complicated until you make it complicated. The ampacities of the conductors here are very much dependent on what we did in dot 22, right? The layering or the how we place them in the tray, and all those type of things will be very dependent on that as well. So in many times you'll see it reference it back to maybe 392.22. And then you'll see it'll make references to certain tables, which will be ampacity tables for a specific application. And so we'll kind of cover that. Now, what we're not going to do in today's episode, which again is some people might not like this when I say this, we're not going to cover every single application in here. We're going to just do a good overview, give you a good understanding, a good grasp of it. And of course, if you have any additional questions after this series, You know how to reach me. My call to action would be for you to get an email out to me at info at masterthenec.com. Or if you want to make it easier, just go to the website. You'll see a contact us button and send me your question. I'm more than happy to try to help answer that question. Okay, so let's start first. 392.80a says this is the ampacity of cables rated 2,000 volts or less in a cable tray. Now, when we say cables, we're also talking about single conductor cables, and we kind of described that in part 1 of this series. But again, it's also talking about single insulated conductors as well. Okay, because again, dot 10 of 392 introduced single insulated conductors. Now, for many years, it never said that. It said single conductor cables. But THHN, THWN, XHHW2 aren't necessarily single conductor cables. They are single insulated conductors. So we did it anyway, but now we have clarity, and they're considered synonymous in the applications here in 392. When they're one larger, that is. Okay. So let's look at the first one, A1, multi-conductor cables, ampacities. We need to start it out first. We need to get this thing started. It says, the ampacity of a multi-conductor cable, nominally rated 2,000 volts or less, installed according to the requirements of 392.22a. Okay, right off the bat, you got to listen to part 1 to understand what it means in 392.22a. What does that mean? I mean, we're making reference to it. Well, that's talking about when you're putting them in the tray, whether it's a ladder tray or ventilated trough cable tray or solid bottom or whatever it is. You've got rules of how you put these conductors in there and the number of conductors that can be in there. So we've established that. So that's why it's referencing back. It's assuming that you've already done that. Now that you have, it'll come back and say, shall be as given in table 310.16 and table 310.18. Subject to 392.80 A1A, A1B, A1C, and 310.14 A2. Okay? So again, you've got your ampacity values that are going to be given to us in 396, which used to be 310.15, excuse me, did I say 396? Excuse me. In 310.16, which used to be 310.15 B16. So we've changed that, obviously, for this code. So we're using the ampacities there. And, of course, you have the values in 310.18 as well. And for those that aren't familiar with 310.18, I'm going to tell you, for most applications, you wouldn't worry about it. But 310.18 is talking about ampacities of insulating conductors where it's not more than 3 current conductors in this application. But if you look at it, this one is telling you dealing with a wiring installed in a 40 degree C, whereas 310.16 is a 30 degree C, and that's probably more of the applications that me and you are used to dealing with. So if you've ever wondered what those two ambient tables are, whether it's 30 or 40, most of our applications are going to be in 310.16 for those ampacity values in that table. And again, not more than 3 current conductors, okay? That's what this table is based on. Now, if you have more than that, then, you're going to have to do some, adjustments for that. Okay, anyway, getting back to the topic, I don't want to stray too far. This is not a derating demystified video, by the way. All right, so basically it's saying you use the ampacities from those tables for these multi-conductor cables, and of course they'll be modified accordingly based on what we're getting ready to go over, which is A, B, and C of 392.80, okay? A1, all right? Number 1, it says, the adjustment factors in 310.15C1 shall apply only to multi-conductor cables with more than 3 current conductors. Okay, let me stop right there. So when you have more than 3 current conductors, we have to do an adjustment, right? And you're familiar with that. In the 2017 code, that was 310.15B, B3A, but now it is 310.15C1, okay? Just kind of reorganization a little bit. So basically it's saying, look, hey, if the cables that I'm putting in this tray, and they don't have more than 3 current conductors, then I'm good. I'm pulling the ampacities from 310.16, and I'm not going to have to do nothing. Okay, that's what it's starting to say. Now, it also reminds you, because you're thinking, well, yeah, Paul, but don't I have a bunch of conductors in this tray? Okay, just relax. We're not there yet. Then it says the adjustment factors shall be limited to the number of current carrying conductors in the cable and not the number of conductors in the cable tray. That's a beautiful thing, right? Because basically what that's saying to me is that, you know what? If I install them in accordance with 392.22a, I follow those rules, I put these multi-conductor cables in there. If I don't have more than 3 current carrying conductors in that individual cable assembly, okay, and in this case, then guess what? I don't have to do any adjustment. I'm perfectly fine. And it's also reminding me that I'm not going to take all of the conductors that are in that cable tray and try to act like they're being bundled, and then I have to apply something in 310.15b3. I don't have to do that. The very last sentence makes it very clear. It exempts cables in a tray from these adjustment penalties, if you will, because, again, they don't have more than 3 current carrying conductors. So, again, I get to forget that 310.15b3a, or, of course, in the 2020 code, it's now 310.15c1, okay? So, again, it also reminds us that I'm also not adding up all of the individual conductors in a tray. If I had to apply adjustments to this application, it would be based on the fact that I had more than 3 current carrying conductors in that cable assembly. But if I don't have more than 3, ain't got to worry about it, okay? So it starts out by saying that. It's a pretty good thing. All right? Everybody with me so far? That's pretty important, I think. All right, let's move on to B. All right, this one is dealing with a continuously covered cable tray. So it's got a cover on it. And here's what it says. Let me read it. It says B. It says, now, where cable trays are continuously covered for more than 6 feet with a solid unventilated covers, okay? Not over 95% of the ampacity of table 310.16 or 310.18 if we're dealing with a situation where I'm dealing with the 40° C application, shall be permitted for multi-conductor cables. So basically, my ampacity value is going to be limited to 95% if I have a continuously covered, unvented cover, solid, more than 6 feet. If it's not more than 6 feet, then I'm pulling my values from 310.16 as normal. Of course, terminal limitations being what they are, keep that in mind. But at the end of the day, it's just kind of making a statement that, well, you know what? If it's a cable tray and you continuously cover it more than 6 feet and it top on it, that covering is solid, there's no vents in it, well, then you're going to limit to not over 95% of the ampacities based on table 310.16. And of course, we do all of our ampacity values based on 310.16. Okay? So that's the second rule. Easy solution to that is make sure that it's not a solid, unvented cover. Might be the easy way around that one. All right, and the last one is, and this one is C, and it says where multi-conductor cables are installed in a single layer in uncovered trays, okay, with a maintained spacing of not less than 1 cable diameter between the cables, the ampacity shall not exceed the ambient temperature corrected ampacities of a multi-conductor cable with not more than 3 insulated conductors rated 0 through 2,000 volts in free air in accordance with 310.14b. Okay? So again, this is applies to a single layer of multi-conductor cables, and of course you've got that cable spacing of 1 cable width, and it's an uncovered tray. If this is the case, then it's telling you that the ampacities have to be calculated based on an engineering requirement in 310.14b, which is basically, when engineers do it, it's kind of like a near McGrath. Usually it's going to be something they calculated out under this allowance here. Okay? And in doing so, it is based on the benefits of what's called a free air condition as well. And it gives you an informational note that says see informative Annex B, Table B2, 3, and it gives you some guidance in that application as well. All right? So anytime it gets one's reference to 310.14b, that's bringing engineering specifications involved and engineering is involved in that ampacity calculation. I can tell you right now, generally that would result in a value that is probably going to be a higher allowance of ampacity than what you'd get in a 310/16 anyway. So most people, if they don't want to do the engineering involved, I'm just kind of throwing this out there, then what ends up happening is they end up just sizing it based on 310/16, and it's more conservative. Obviously, in a design, talk to your engineer, your designer, whoever's doing it. If you're the engineering designer and you're doing that, just remember 310/16 values are pretty darn conservative, okay? The other thing that I will mention is it states up at the very beginning 310/14A2, okay? And you're probably thinking, well, are you going to discuss that? And the answer is yes. And what does that mean? All right, now, in the 2017 code, this was referenced as 310/15A2. So we had some changes in the code, reorganization. So this bumped this one to 310/14A2, where it used to be, again, 310/15A2. And this is that 10-foot, 10% rule. So I'm going to read it to you because, again, it could be useful for conductors that are in a cable tray. And depending on where it's installed, maybe ambient temperatures are playing an effect and can change the ampacity of a portion of the conductors that are in a tray. It says, because again, ambience, even though we've been talking about the number of conductors and whether or not an adjustment, you still might have a correction based on ambience. I mean, don't forget that. And here's what it's saying. It says, where more than one, again, we're talking about 310/14A2 because I want to be able to tell you what that means. It says, well, more than one ampacity applies to a given circuit length, the lowest value shall be used. Okay, but that means that if I have a conductor that's good for a certain ampacity, and now I run it through an area with an elevated temperature that's now going to reduce the ampacity for that conductor in that area, basically I have to protect it at the lowest value, which is going to pretty much suck. Because I got a conductor that's not subject to it that has a higher ampacity. And I'm like, well, you telling me I can't use that higher value? Okay, maybe it's good for 30, but I put it in this area, it drops it all the way down to 20. And you're like, really? Well, there's an exception. And the exception says, where different ampacities apply to portions of the circuit, it says the higher ampacity shall be permitted to be used if the total portions of the circuit with the lower value does not exceed the lesser of 10 foot or 10% of the total circuit. So if that portion that was lower, and remember, keeping with my example, at 30 amps, and then it's going through an area with an elevated temperature that drops it down to, let's say, 20 amps, if that portion there that's dropping it down, if that is not more than 10% or 10 foot, whichever is, in this application, I need to think about this portion, that if it is the lesser of the 10% or 10 foot, okay, comparing the two, of the total circuit, then I get to discount that lower value and say, okay, that small area with the heat and that's affecting my ampacity, I get to forget that's even there. I just throw that away. I just ignore it. But again, a good example of this in a 100-foot run, okay? And the reason we give you 10 foot or 10%, because let's just use an example. If it's a 100-foot run, 10% is 10 feet. Well, that equates to 10% or 10 feet. They're both identical. But when we go with something that might be less than 100 feet, then the 10 foot would be greater than maybe the 10%. And I have to take the lesser. So I have to take the 10% value. And as long as that value is the lower value, then I get to discount it and say, forget it. It's not going to affect my ampacity, and I get to kind of, so it's a beautiful thing, and it's used a lot in the code, okay? And to be able to do that. And it's based on the fact that that area with the reduced ampacity because of maybe a condition of use, maybe an elevated temperature, that, again, heat is not good for a conductor, okay? We're trying to limit the heat anyway so we don't violate the insulation rating. So, usually one of the things we do is reduce the amount of current that can be on it. Well, if I've got other areas of the conductor that I want to use that value, that would suck. So again, thank God for 310.14a2 that we have that ability in the code. And I'm going to tell you, as a wire manufacturer, the reason you get this is because when you're running those conductors, it actually uses the entire conductor as a heat sink. So even though you have that area with the elevated, it will pull that heat away, and it will balance out. It's not going to be a big concern when you utilize it. Now, there are areas where it tells you cannot use this allowance. And so if a specific section says that you cannot utilize the benefits of 310.14a2, then it's kind of, that would suck too, because you're out of luck. But in this case, trays, we're okay. We're able to use that, and that's what it's saying in 392.80a1, dealing with the multiconductor cables. Okay? All right. So we kind of get the gist of this. I've kind of given you some opinions of that and how you would address it. Now let's go on to what's called single conductor cables, and we're talking with ampacity, and we'll kind of talk a little bit about it. Okay? Now, here's what it says under 392.80a2. And remember, when we're saying single conductor cables, we're also assuming that we're talking about single insulated conductors, and we're also assuming that we've got a industrial establishment, because that's the only place that single conductor cables or single insulated conductors can be installed in a cable tray. You with me? All right. So it says, and if you don't get that, you need to go back and listen to part 1, because I went into extreme detail on that. And again, stop what you're doing, go listen to that one, mark what point you have listened into this one so you don't lose what you've done, and then come back to it, speed up to it, and keep on getting it. All right, let's read it. It says, the ampacity of single conductor cables shall be permitted by 310.14a2, which we kind of went over that. Okay? That's a beautiful thing. All right? It says the adjustment factors in 310.15c1, again, that's for the more than 3 current carrying conductors, shall not apply to the ampacity of cables in cable trays. Wow. Talk about, I don't even know if I have a sound effect for that to even, maybe I've got this. Wow. Now, before you get really, really, really excited, we got to read on, because you are going to get some rules, okay? Everybody gets excited. It's like, geez, man, I ain't got to do no daggone, dealings with 310.15c1. Remember, that's adjustment factor. You still might have an ambient issue, so God, don't forget that. Even though we're talking so much about this, you still might have ambient. But we're just talking at this point, I'll put in there, because the conductors were installed in a specific way, and we're going to meet some rules here in a minute that you got to follow, so don't get too awful excited. Now, it says the ampacity of single conductor cables or single conductors cabled together, whether it's triplexed, quadplexed, and whatever, nominally rated 2,000 volts or less, shall comply with the following. Okay, now is where you get the, yes, we've got some rules we got to follow. So let's make sure we read them, and we got a better understanding now, because we started off thinking, crap, man, we ain't got to do jack. We can use the lesser of 10 foot 10%, where there's 2 different ampacity values. Boom, we get to not worry about the adjustment factors for the conductors in a cable tray, single conductor cables in there. Boom, we're thinking we're really kicking it. Now we're going to get into some A, B, and C, and D applications, okay? So again, this is going to also help control the ampacity values, and that's why we don't have to use the allowances or the more restrictive 310.15c1, which incidentally, if you're in the 2017 code, that was 310.15b3a. Okay, keeping consistent. I don't know what code cycle you have in your hand. Hopefully, it's a 2020. All right, now let's look at A, B, C, and D. Okay, again, remember, we're dealing with single conductor cables, or in this case, single insulated conductors as well. All right, A says, and again, we're going to rely on the fact at this point that you have actually listened to part 1, because we spent a lot of time understanding when we have single conductor cables in a cable tray, how we're supposed to install them, whether they're layered or whether they're dealing with circular mill or the actual cross-sectional area, depending on the amount of fill, dealing with size conductors we're talking about. I'm not going to rehash that. And I know you want me to, but I am not. You need to go back and listen to part 1. Okay? It's just usually out of context for me, because usually I regurgitate it over and over and over again till the audio podcast is 2.5 hours long, but I'm not going to do it today. Okay, now it says, where installed according to the requirements of 392.22b, again, that's talking about whether or not it's single layer, spacing, whatever it would be. It says the ampacities of 600 kcmil and larger single conductor cables, or in this case also single insulated conductors, in uncovered cable trays shall not exceed 75% of the ampacities in table 310.17 and table 310.19. All right, so you're saying, what, Paul, why didn't it send me back to 310.16? Well, this is a beautiful thing here. If it's 600 and larger and you install them based on those sizes in 392.22b and it's an uncovered cable tray, then I am going to limit the ampacity to 75% of 310.17. And of course, 310.19 is again, but that's difference in that one is that's dealing with wiring installed in a 40 degrees C ambient. And mostly what me and you are going to do is in a 30 degrees C ambient. That's generally the one we're going to use. Okay. So again, it's saying that, so it's limited to 75%. Now, in the surface, let me just give you an example, just so we can take this into context. If I look at a 600 kc mil under 310.16, it's just say copper, for example, and you can do it with me. A 75 degrees C column, a 600 is 420 amperes. Okay. And if I look in 17, a 600 into the same column is 690 amperes. Wow. So 420, 690, I'm getting a huge benefit by this thing we call free air, right? Okay. So again, interesting enough, we do have a definition of what free air is. But the interesting thing here is that it's directly telling me the table that I use. So I'm not questioning it. I'm not. As long as they're 600 kc mil and larger, and I've installed them properly in accordance with 392.22b, I ain't asking any questions. But before you get all excited, you got to remember, you can only do it to 75% of that 690. Okay? So how does that equate? Well, that ends up being, 690 times 70%, 75%, it's 517.5 amps. Well, we got all excited, but at the end of the day, it's still more than the 420 that's listed in 310.16. So hey, it's something, right? Don't kick a gift horse in the mouth. I'm just saying. All right, so again, for that. Now, it keeps on going. And that was an uncovered cable tray. It says, now, where the cable trays are continuously covered for more than 6 feet, so that seems to be the trigger here, more than 6 feet, continuously. So I guess if you break it up a little bit when you put covers on it and don't make it 6 feet continuous, then you're okay. It says, with a solid unvented cover. All right, so give me a vented one and I'll get away from this. If it is that case, it says the ampacities for 600 kc mil and larger cable shall not exceed 70% of the values of the ampacity values in table 310.17. Okay, and of course, if you're dealing with an application that is 40 degrees C, that's 310.19. But again, for all intents and purposes, we're going to use 310.16 and 310.17 for most of our applications. But in this case, we're using 310.17. It has a higher value, and it's dealing with free air. All right, so that's what you're dealing with those. Now let's keep on getting it because we're making good progress here. Now B, what is B? It says now where installed according to the requirements in 392.22b, the ampass, again following those rules in B, that's the layers and spacing and how you install it. Again, go back, listen to part 1. It says the ampacities for 1/0 AWG through 500 single conductor cables, and again, single insulated conductors would fall here now based on 2020, in uncovered cable trays shall not exceed 65% of the ampacities in 31017. All right, so, okay, so it's pretty cut and dry, right? I installed them in the tray in accordance with 392.22b, and I think I'm good. Now I'm trying to determine what the ampacities are. And obviously, in this case, it's an uncovered tray. I'm going to get the benefits of utilizing this 31017's ampacities. But now that I'm dealing with a continuously covered, and it might be more than 6 feet, and it's unventilated, solid cover, well, from 1 through 500 kc mil, I'm going to have a bit more reduction here. It's going to be 60% of the ampacities in those tables. 31017 for free air application. All right, so we're good there. Now, we got to start moving down a little bit. So we get to C, where single conductors, or again, single insulated conductors, are installed in a single layer, okay, in an uncovered cable tray. And then remember, 392.22 is going to talk about sizing and when it needs to be a single layer and all that. So this is stating that you already established that in your installation, and it ends up being a single layer. It says we're installed in a single layer of uncovered cable tray with the maintained spacing of not less than 1 cable diameter between individual conductors. The ampacity of 1/0 AWG and larger cables shall not exceed the ampacities in table 310.17. So when you start getting into this single layer and you meet the spacing requirements, you're going to allow for air, you're going to allow for circulation in that scenario. Okay? And once you get into that, and we're again, dealing on the size of the conductors, then I get the benefit of using the full values in 310.17. Again, I might have an ambient temperature I got to worry about, okay? But again, I'm not dealing with anything at this point with the adjustment factors, because this already has its own allowances, and the spacing allows separation and things like that, okay? So again, makes it easy to follow. No questions here. Okay, now you're going to bring back to that question, well, what about those configurations that you talked about earlier, Paul, the triplex, quadplex, what about those? Okay, all right, well, then that's when we get D. And D says this: where single conductors are installed in a triangular or square configuration in an uncovered cable tray with a maintained free airspace of not less than 2.15 times 1 conductor diameter. Okay, so it's it's the largest conductor contained within that configuration. So 2.15 times the OD of that largest conductor contained within that configuration. Okay, the ampacity of 1/0 AWG and larger cables shall not exceed the ampacities of 2 or 3 single insulated conductors rated 0 to 2,000 volts supported on a messenger in accordance with 310.15. So I know right now you're just scratching your head and saying, what the crap did he just say? All right, so if I'm taking the single conductors and I'm arranging them in triangle or diamond or square shape, whatever, and as long as I maintain the free spacing, which is 2.15 times the largest conductor diameter in the bundle, and so that's create a spacing, and the ampacities for a 1/0 and larger conductor, okay, well, basically they can be calculated based on the 2 or 3 conductor in the bundle that is typically used on a messenger. And so this effectively sends me back to utilizing table 310.20. And that is dealing with ampacity of conductors on a messenger. And you have ampacity values here. So again, it allows me to use these values. It kind of indirectly pulls this in. Now, the interesting thing about this is this one's based on 40 degrees C. Obviously, your application would be 30 degrees C. So it just reminds you that you need to think about the factors when the ambient temperature is not 40 degrees C. And of course, you would make an adjustment for that, and it gives you instructions on how you would do that. And the engineer is more than likely going to do that. And make that change. But this is allowing you to be able to use that value as if it was on a messenger. And so, again, in that same context, what we were talking about, I'm just going to look at it. And let's just say it's 75 degrees C, it's a messenger, it's copper. Let's just do it 553 amperes. Okay, so that's what would be for a 600 kc mill. All right. So, I mean, that's larger than whatnot. So, again, that's just giving you some allowances to be able to use other tables. Also, remember that if all else fails and you're really, really confused, you can't really go wrong by utilizing 31016. Okay? It's going to be more conservative. All right? If it's being utilized as, it's hard for it to be considered free air because it's bundled. Now, the messenger reference that we're kind of getting to in 310.20 is concept on a messenger, and we have hired, again, it has to do with air movement and all this kind of stuff that pulls these general messenger rules in. But at the end of the day, the code is just allowing you to do that. Don't overthink it. But in an effort to make sure that if you don't understand how this is applied, using the messenger allowance here in 310.20 for the 2020 code. Incidentally, for the 2017 code, it's 310.15B20, by the way. So, again, one of those things to just keep in mind, if all else fails, then revert back to, my opinion, is revert back to the ampacity values of 310.16, and you're not going to run a risk of violating the insulations rating due to the current that's being on there that could cause a problem. I'm just saying. I'm just talking in practical layman's you and me terms. Engineers will know how to do this differently. Engineers will take advantage of the configuration with a triad or in a quad, if you will. They will attempt to take advantage of that, and that is fine as long as they're following all the rules that are associated with that and taking everything into consideration. If the temperature is other than 40 degrees C, then they're going to have a correction factor that is going to change based on the ambient temperature, and they're going to have to use the formula for that to be able to do that, okay? All right, so keep that in mind. And again, if it's more than 3 current conductors, then you're still going to have to reference 310.15C1, okay? This is an application where it just told you based on 2 or 3, so I still don't have more than 3 current conductors. You with me? All right, that was, I don't know if that was I guess that wasn't as painful as it could have been. Could have been real painful, I guess. But anyway. Okay. Let's see here. What else do I want to talk about in this episode? You know what? I should also mention that, again, the utilization of 310.20, that messenger application for this unique situation in triad or triplex, quadplex in a tray, and utilizing the messenger allowance for the ampacity, again, remember, there can't be more than 3 single insulated conductors to be able to utilize this, okay? So, again, I don't know if I said quad, but, again, in order to use this one, it basically point blank says that I am, in order to be able to do that, again, you have the general rule at the beginning for spacing, right? And that still applies. But if you're going to use the ampacities that are afforded you in 1 aught and larger, when it comes to using the messenger application, then it can't be more than 3 conductors in the bundle, okay? Nothing says that I can't have a quad in there, okay? But if I do that, I'm going to have to do my ampacity values based on what we've done all up to this stage, okay? And keep that in mind, okay? But I do get an allowance for triangular or diamond configuration, triangular configurations of 3 conductors or less. Then if I do the spacing and follow all that, then I have an allowance that I can apply. But again, you still could have 4 conductors, right? It just says not more than 3 insulating conductors. I can't have 4. One of them is uninsulated. Okay, I think you get it. All right. Next, let's kind of look at what's the deal is when you have a combination. So what if I have multi-conductors and single conductors in the same application for ampacity? Okay, well, doesn't get more confusing, but it's just something that you have to think about. And so we're going to touch on it because, again, you could very easily have multi-conductor configurations in the tray, as we saw earlier in 392.22, but also single conductor cables in there as well. So how will we address the ampacities on that? All right, the first way to think about this is to take each one of them individually. So let's go on and read it, and then we'll try to digest it. So 392.80 A3 says combination of multiconductor and single conductor cables. So now it says where a cable tray contains a combination of multiconductor and single conductor cables, the ampacities shall be as given in 392.80 A1 for multiconductor cables. So we do just what we did anyway. We don't do anything special. We treat it the same way we just calculated a minute ago for that. And then it says to use and 392.80 A2 for single conductor cables. And we did that just a second ago. So far it's looking like we treat each set separate. The multi-conductor cable ampacities treat in accordance with 392 A1. And then the single conductor cables we treat in accordance with 392.80 A2. That sounds real simple so far. Okay, just forget that the other one exists and do your calculations based on this one and then that type of thing. So far it seems pretty simple. Okay, however, using this allowance, using this statement to keep it that simple, only applies if, one, the multi-conductor fill per 392.22a, which is all the work that we did in part one, and then is expressed as a percentage of the total allowable fill in the cable tray. Okay, we get a value, and that's a percentage, and we know what that is based on whatever we're putting in there for the cable. We already established how to do that. And then two, the single conductor fill that we talk about in 392.22b is then expressed as a percentage of the total allowable fill in the cable tray. And together, three, the total adding together is not over 100%. Okay? So, seems pretty simple so far, but again, we need to know what percentage fill of the tray we have based on both applications of putting those conductors or those cables in those trays. Okay? So, that seems pretty simple so far. And basically, if you think about this, how you configure those conductors in the tray, because you do have to remember there are rules that we have to follow in 392.20 that we didn't talk about, and that is when you're paralleling, you have to you're grouping, each phase, neutral, and or grounded conductor and equipment grounded conductor if it's there, and how you bound those groups together. And so once we establish how we're putting them in there and we follow the rules, and that's, again, the example where I can do single conductors and I put them, let's say, in a, maybe I configure them in a grouping, when I'm doing that, again, we're talking also about making sure they're lashed down. For example, single conductors are lashed down when they're in the group to prevent excessive movement due to fault current, the magnetic forces that can take place. Okay? Unless, of course, single conductors are cabled together, such as in a triplex, then they're already connected together and they're acting as one. Okay? So anyway, in that concept, what we did before is we need to come up with what the fill is for the cables and what the fill is for the single conductor cables. And as long as that sum, adding the two together, the percentages of fill doesn't exceed 100%, okay, then, based on the percentage values that you get, then we're okay. Then you can just treat each one independently, not overcomplicate it, and walk away. You know what I'm saying? All right, so again, don't want to overcomplicate that, but in most cases, I think what's going to happen is you got to follow the rules for 392.22a for single conductors, for cables, and 392.22b for single conductors. You're going to have to come up with their allowable fill or their percentage of fill for each at this stage, in order to quantify that I can calculate the ampacity on each of them separately. And then follow the normal rules that we follow in 392.80A, A1, or A2 accordingly, whether we're dealing with cables or single conductor. I won't overthink this one because I think in most cases, if you follow the rules in 392.22A and B, that even when you add up the cross-sectional area and percentage of fill for both the single conductors as well as the cables, you're not going to exceed 100% of the value for that cable tray. So again, if that's the case, then you just treat each one of them separately. They'll have their own ampacity values accordingly. The only thing that after all of that to remind you is that just take your time and calculate them out. Okay? Don't overthink it. All right? All right, so the only other thing after that, guys, is dealing with medium voltage and things like that, and I am not going to get into 2001 volts and over. Just not my bailiwick today. Not going to get involved in that. So anyway, hopefully you got something out of part 2. We covered as much as we could cover, and hopefully I've not totally confused you. But of course, in the case that I did, you can always email me for clarification. I'm not perfect, okay? I'm kind of doing these shows on the fly. I don't have any, as you can tell, I don't really have any study guide. People have said, Paul, you just kind of go all over the place. Well, I have ADHD. I know this. I've had it for my whole life. But I'm doing my best to work with it and try to teach you something. So again, you can always email me at info. That's INFO, like information. So it's info@masterthenec.com. And I'm more than happy to answer any question, add clarity, interact with me. Go to our website, listen to our videos, listen to our podcasts, go to our Facebook pages, Master the NEC Exam Prep or Master the NEC in general. If you want to subscribe to our 2020 code changes, or actually it's the 2020 code itself, where we examine every single article in detail in every section, then that would be over on our Patreon. And to find out how you can join our Patreon, just go to paulabernathy.com and you can join it, or go to masterthenec.com, and up at the top left, you'll see a little Patreon button. Click it and you'll get more information on how to become a subscriber. We appreciate your patronage. And until next time, folks, stay safe and God bless.
Shut up and sit down.